Hello everyone. In this video I would like to try to explain how I constructed the clock and the Nixie time display. There were only two things actually I wanted to accomplish, and those were to use only relays as active components and to make the clock work in the 24-hour format. The easiest way to build a binary counter is to use T flip-flops. The T here stands for toggle, and simply chain them to form a ripple counter, also known as an asynchronous counter. So this is how such a counter counts. All it actually does is to divide the clock signal further and further, which results in these various bit combinations, which ultimately form the byte representing a decimal number. Here's the same thing again in table form. On the left here you can see the output of each flip-flop. In the middle, the binary value those outputs form together. And here's the decimal value of each of those 4-bit long bytes here. The first thing I had to do was to develop a circuit for a T flip-flop with a minimum parts count. I found some useful circuits on the internet, modified them a little, did some testing, and this is what I ultimately came up with in the end. Just 2 relays, 2 resistors, and 1 capacitor per flip-flop. What's important to know about this circuit is that ground level means logical 1. So everything that's not ground level, including floating levels, like the output is here right now, is not a logical 1, but a 0. So this is the flip-flop in its initial state. The 3 points here, here, and here are connected to plus 12 volts, and the 4 points here, 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 and here are connected to ground. What happens now is that the current in this part of the circuit here is limited by this resistor, which means the capacitor down here is being slowly charged, which is not important right now, but it also means that the coil of relay number 2 here is just somewhat energized, but not quite enough to actually make the relay activate and the switches to close. So now we apply a bit to the input down here, which means connecting it to ground level. This being a toggle flip-flop, we do this just briefly, say for 200 milliseconds or something like that. The coil of relay number 1 here is energized, the switch is closed. This upper switch here is not used in the circuit, but the lower switch connects the capacitor to the 12-volt rail here. This resistor up here is just there to limit the current flowing into the capacitor a little bit. But the brief time it's connected to 12 volt is enough to give it a full charge. So now we remove the bit again from the input. Relay 1 falls off. The 2 switches go back to their normal positions. Our capacitor here, being fully charged, releases its energy over this line through the coil of relay number 2. And we remember that the coil was already pre-energized by the current flowing through the resistor here. And the additional current from the capacitor is now just enough to make the relay fully energized and to make it flip over. Then, after the capacitor's charge is gone, the limited current coming through the resistor is still enough to keep the relay latched, even though just slightly. This is also why the value of this resistor here is the only critical value in the circuit. Also I had to find out that not all the relays are alike. There are some tolerances, which meant I had to play with the values of the resistor here a bit. Sometimes add or take a few ohms for some of the flip-flops to make it latch and release consistently. So now we are going to reset the flip-flop Again, we apply our bit down here for a brief moment, making relay 1 activate. This connects the capacitor through this path here right to ground, draining off all the charge that may have been left in it. The bit at the input is removed, relay number 1 falls off. What happens now is that the completely discharged capacitor is connected to this part of the circuit here. Being so empty, initially it pulls a quite large amount of current through here, and this makes the current in the coil of relay number 2 here dip for a short moment. And we remember that the relay was in a state of just staying active and not falling off due to its current being limited by our resistor here. So that brief dip in current now is enough to make it click back to its idle position. And finally, both relays are again in their initial position, and so is the flip-flop. The next step was to find out how many flip-flops and relays I will actually need. These here are the two time values with the highest single digits, and using the power of 2 formula we can calculate how many values we can represent with any given number of bits. So with 2 bits we can represent up to 4 values, 3 bits 8 values, and 4 bit 16 values. 2 being the highest number that the tens of the hours can be, we get by with just 2 bits for this digit. For the ones of the hours, it's the number 9, so we do need 4 bits, even though it would enable us to count up to 16. But with just 3 bits, we could get to count to only 8, which is not enough. However, 3 bits are enough to count to 5 for the tens of the minutes and seconds here. And for the ones of the minutes and seconds, each will need a 4-bit counter again, because we are going to count to 9. You will have noticed that the counters do count further than we actually need, so we will have to add a reset circuit that resets the counter when a specific value is reached. For this I've used a great piece of software called Logic Friday. You can find it if you Google it. In Logic Friday you can enter truth tables. Let's take the 4-bit counter as an example. This is its truth table. On the left side we see the decimal representation of the binary value here in the middle. And on the right side, that's the output of our reset circuit. The circuit itself will do nothing more than simply interrupting the power of the whole 4-bit counter, making all the relays fall off and therefore reset the counter to 0. I will talk a bit more about that part of the clock a bit later. So we want the counter to count from 0 to 9, and then as it would reach number 10, get reset to 0. You can see here what I've entered into the truth table. The reset circuit's output is 0, but then when the counter reaches 10, we want it to be 1. All the higher values here, they will never occur, so I told the Logic Friday software to simply ignore them. Now we use a function of Logic Friday that's called minimization. What we see here is our condition that we've entered. This is just a bit pattern for a decimal 10, 1, 0, 1, 0. What Logic Friday does now is finding out the shortest unique bit pattern for this value, our decimal 10. So the combination of bit A and bit C, both having the value of a logical 1 at the same time, never appears before the counter reaches 10. This means that for our reset circuit, it's enough to keep an eye on those 2 bits and reset the counter as soon as they both are a logical 1. I did this for all the counters, and the result was that they all need a single AND gate with 2 inputs and 1 output to trigger the reset. Having this sorted out, I could finally calculate how many relays I actually will need. Here on the left side are the counters. We remember that each flip-flop consists of 2 relays, so each bit means 2 relays. And for the AND gates, each is made of 2 relays as well. Again, I will show you a bit later how the reset circuit actually looks. And this all ends up to the clockwork itself containing exactly 52 relays. As promised, this is the reset circuit. Here we have the 2 relays. Both coils are connected to plus 12 volts together. The other ends of each coil form our inputs A and B. We can see that the common contact of each of the relay switches are all connected to ground, whereas the switches up here are connected in series. Those down here are connected in parallel. This output here is the common ground connection of all the flip-flops in the counter. Means if this line is interrupted, all the flip-flops fall off, resetting the whole counter to 0. This output up here simply connects to ground when the AND condition is fulfilled. The use of this is to give a pulse, a high bit, to the next counter, making it advance. This happens when, say, the ones of the seconds have counted to 9, and therefore the tens of the seconds have to advance from 0 to 1. So the condition being shown here is both inputs being 0, means not connected to ground. Down here in the corner, I did a small scribble of an idea that I had, which would later prove itself to be mandatory. I put some large value capacitors over the 2 relay coils here, making them stay active a little longer even after the reset of the counter has already been triggered. Without them, the interruption of the ground line was too short for all the relays to fall off. Reset didn't work properly, and neither did the advancement of the next higher counter with the pulse that should appear at this output here. Here we can see what happens when condition A is true, condition B is false. The relay here is active, the switches are pulled. Ground connection here is not established, means there is no pulse to the next counter, but ground connection here is still available through this path here, means for the flip-flops in the counter, nothing has changed. Same thing's the case here when condition B is true and condition A is not. No ground connection here. Ground connection here is still available through this path. But when both conditions are true, we have ground connection here, means the next counter is advanced. Ground here is interrupted, means the counter is reset because all the relays fall off. Knowing I will have to build quite a few of them, I came up with this connection layout of the flip-flops. This is how I wired up the power. The relay coils need 12 volts, but the incandescent light bulbs for the display need just 3 volts. So the relays and the bulbs share a common ground, but each have their separate positive rails. So after all this was sorted out, I started drawing some sketches of how the whole thing is going to look. Sorry, drawing is not really one of my strengths. And then started sourcing materials, creating drill patterns, drilling a million holes and putting it all together. As for the Nixie display, I had to modify the main clock first and add an extension port where all the bits are available. I did this with one of these things here. They are readily available, and so are the cables. And 25 pins are enough for all the signals. Here is the pinout of said extension port, and even though it's in German, I think you get the idea. The large gray area up here are all the bits, so the time information itself. Pins 21 and 22 are the clock signal. All we actually need this for is for the .Nixie tube to flash in the rhythm of the seconds. Pin 23 is empty, and the remaining 2 pins plus the cable shield are used for ground return. This is how the two devices are connected. Please note that this is kind of simplified, it's just for explanation. The main clock can run standalone. Its relays get their power straight from the clock's internal power supply. Of course, the relay coils aren't hardwired to the power supply as it is shown here. This is just about the principle. The Nixie display's power line structure, however, is a little different. Its relays get their plus 12 volts straight from the power supply as well, but the minus 12 volts, the ground line, takes a detour. It's connected to the main clock's common ground over the extension cable here between the two devices. We remember in this architecture, the ground line is what matters. It being present or not is what makes the difference between a 1 and a 0. So to make a long story short, the ground connection of the Nixie display's relays is switched by the main clock relays. So like this, we have successfully transferred the digital time information from one device to the other. I could not control the Nixie display's relays here directly. They are quite massive relays that draw quite some current, and neither the flimsy wires in the extension cable nor the wiring in the main clock could have handled that. Yeah, like the relays I've used in the main clock, I chose these relays because they were the cheapest relays I could get in large amounts that suited my purposes, and also I kind of just like the looks of them. So what I did is add an array of relays down here with low power coils but high switching capacity. Yeah, there are the little black relays at the bottom of the device labeled as repeater, as you can see down here. So Nixie tubes are really nice because they are simple to use. Just connect the common plate to a high voltage supply over a resistor of the correct value, and then connect the pin of the number you would like to light up to ground, and that's it. Each number has its own pin, not like those 7-segment displays where you always have to power a specific combination of segments to display a digit. This, plus the looks of them, of course, make the Nixie tube perfect for this kind of clock. So what do we need now? Not much actually, just some basic binary to decimal decoder, and such a decoder is nothing more than a matrix of AND gates. So what do? We start up our trusty old Logic Friday software and begin entering truth tables. This here is the table for a byte of 4 bits. We can see that here we have our 4 inputs for the 4 bits, and we have 9 outputs for the digits from 0 to 9. All the values above 9 are ignored because they are never going to happen. Now this is the minimized version of the truth table we have just seen. So this represents the actual AND gates we will have to build for decoding a 4-bit binary coded decimal number into actual decimal numbers. We can see 2 arrays with 4 inputs each, 6 arrays with 3 inputs each, and 2 arrays with just 2 inputs each. As each input means one relay, this results in a total of exactly 30 relays. I did some quick math and realized I'm going to need a lot of relays. This and the fact that I had these nice 4-pole double throw relays here left from an earlier project made me come to the decision that I'm going to build a display with 4 digits only, but switchable between the two modes, hours and minutes, and seconds only. With the full 6 digits, I would have been at way over 100 relays, and that just seemed a bit excessive. So the 2 relays have 8 poles in total, and I used to switch the 3 bits of the minutes and seconds tens and the 4 bits of the minutes and seconds ones. This leaves one contact free, which is used to cut the high voltage supply to the 2 leftmost tubes in order to make them go dark, while the seconds are being displayed on the 2 rightmost tubes. Here we have one of the logic units of a decoder for a byte of 4 bits, namely the one for the digit 1. What we see here is the circuit with all the inputs being 0, means the digit being currently displayed on the clock is actually a 0. When we look at how the relays are connected, we see that their switches here are connected in series. Relay A is conducting only when it is not active, means when there's a 0 present at its input down here. Otherwise, it will interrupt the line. This is the case for relays B and C as well, only relay D is different. It will actually keep the line interrupted until it is active, meaning there's a 1 present at its input down here. So as a result, this zeros connection here is only closed when bits A, B, and C are 0 and bit D is 1. Our truth table tells us that this is the bit pattern for the digit 1. Any other digit will not cause this pattern to appear at the circuit's inputs down here. The Nixie Tube's cathode for the digit 1 is connected to this point here, so it will only light up when the binary code for a decimal 1 is present, because then it's connected to ground. Otherwise, it will always remain dark. What I did next was some planning of the appearance of the device. This is the relay pattern for one of the 4-bit decoders. I wanted the relays to be mounted in a symmetrical pattern, so this is the end result. Each circle represents a relay. The one that's marked red is the final relay of the unit where the tube's cathode will be connected to. Finally, a word or two on the power supply for the Nixie tubes. The tubes need a DC high voltage power source, anything from about 180 to 250 or even 300 volts is fine. The only thing to be careful about is the right value of the resistor between the power supply and the tube's plate. This value should be calculated and depends on the recommended current for the tube and the supply voltage. The current can be found in the tube's data sheet, and the supply voltage is whatever your power supply spits out, so I would say just measure it. A relatively safe way to obtain high voltage, which is isolated from the mains, is to connect 2 transformers back to back. Just use a combination of transformers that give you roughly 150 volts AC at the output. In my case, I've used a 230 to 9 volts transformer for stepping down and a 15 volts to 230 volts transformer for stepping up. This results in an output voltage of around 140 volts AC. According to this formula up here, after rectifying the AC and smoothing, we will end up with about 200 volts of DC here in the end, which is perfect for the tubes. All right, I hope you were able to follow me through this and got some insight on how this thing came to be and how it actually works. If you have any questions, just post them in the comments section and I will try to answer them. I am thinking about building a third module for the clock. I was always really annoyed by the noise this motor generating the clock signal makes. It really distracts me from listening to those relay sounds, so it just has to go. The idea is to build an electromagnetic pendulum to generate the clock pulses. In case it will be a success, I will certainly make sure to make a video about it.